So let's take another look at curvature. So as you can see, we have one parameterization of our curve, and then hypothetically we have another one with respect to arc length parameter. The rate parameterization appears through our change of variables, expressed here on the diagram with the letter G. So T is the directional parameter, and this is so this is our original parametric curve, and then we replace it hypothetically with a more ideal situation, and that is the arc length parameter, which gives us the unit speed. So that's not entirely an ideal way of doing it, even though this would pretty much solve the problem here of hypothetically solved. As you can see, the new parameterization G is the composition of f with that function G lowercase. Okay, and then through the application of the chain rule, we have acquired a condition on the on that change of variables. Okay, so this is the change of variables. Okay, so which is what is it? G equal G of S. Okay, so so as you can see, the condition that we end up with is this. It is somewhat complex. So the derivative of G with respect to, well, derivative of G is, let's rewrite this in a more this condition in a more perfect way. In fact, let's rewrite it in the way that is familiar from calculus 1, because what we're talking about here is related rates. This little diagram is related rate. It is the composition of two functions producing the curve, but it's really about three quantities related by these functions, and their rates of change are related to each other through all those functions. And we have, according to the chain rule, we have our condition. So let me do that one more time. So we have S and T. Well, S in T or T. The transition is actually possible in either direction. So this is my P being point of our space. Okay, and then what I want to do is I want to express this in terms of using the Leibniz notation for these quantities, variables, rather than the functions. Okay, so it's certainly the same thing, except just expressed in a slightly different way. And I also want to go in I want to actually go in the opposite direction. So this turns out to be an easier way to analyze. So in other words, certainly T is a function of S, S is a function of T. Why is it either? We can go either way, because the change of variables is simply one-to-one onto. Once again, let me write that just in case. It is actually an important point here. So if I write f of G of S is equal to G of S. So that is the substitution. So why is it important that one-to-one onto? It's like, remember that thing about retiming your video, that you don't want to switch it back. You don't want to go back, otherwise you'll screw up all your analysis. So G is one-to-one onto, which is why it has the inverse. So it's invertible, and so G inverse exists, and that's why we can go back both ways, from T to S, from S to T. Okay, so then I could just as well express it in the opposite way to what we had. And once again, let me just go with the chain rule. So I'm going to be looking at GF not what I have on the right, but rather I will look in dp dt. Okay, dp dt is the product of the derivative of the other two functions. So it will be simply dp ds dt. Okay. So each arrow will produce one of the derivatives. Just make sure that you go in the right direction, and we when in doubt, always check out that when you're applying the chain rule, there's a possibility, hypothetical possibility that you can cancel. Okay, so if you can, then you probably have it right. Okay, so that is my the derivative. Okay, and then what is so special about our choice of the new variable is the PDX. It is equal to 1, or not equal to 1, but rather its magnitude is. This one is just the one vertical line on each side, because it is a numerical function, so it will be simply ds dt. And in fact, if you don't really need anything else, because ultimately this is simply if you choose of g being an increasing function, then the derivative will be positive. So it certainly matters, the differentiability matters, so I just don't want to repeat that. But the function is differentiable, and the condition that we ended up with is the result of this differentiation, assuming all the functions are differentiable. Okay, so then dp dt is nothing but simply our derivative. Okay, but we're really not. Well, let's rewrite. So rewrite. I have then my ds dt. ds is what we're after all. What is the arc length parameter, and the arc length parameter is what satisfies our the following equation. Okay, so that's a very nice way to rewrite that our condition that we had last time. So the derivative of the new variable, the arc length parameter, with respect to the old variable, so new old is equal to the speed. Okay, so if you realize that if our speed was 1 to begin with, then what? ds dt is equal to 1. What's the meaning of that?
It's uniform speed. I mean, we still have f prime equal to 1.
It is, but simply put s equal to t, right? ds dt is equal to 1 for every value. It's the same thing. So the speed is equal to 1 means that we already have the arc length parameter. Okay, so the result is certainly is confirming what we already know. Okay, now. So now let's have the proper definition of the curvature. So the curvature is a curve is the derivative of the unit tangent vector with respect to the arc length parameter. It's a little bit convoluted in comparison to what we had. What we had, we just said, suppose it is an arc length parameter to begin with, then let's just take then the second derivative, the magnitude. The magnitude of the derivative of the unit vector. So the way we defined originally, we just say, suppose we have our length parameter parameterization. In other words, this thing is already 1. Then just take the second derivative and then the magnitude. That's the curvature. Okay, this one's slightly different because the point is to try to avoid actually using the arc length parameter, but rather operate entirely within the original parameter t. Okay, so then if we rewrite this statement in just algebraically, that you'll see the point. So unit vector is denoted by t, and so it's a function. You can say it's a parameter curve, but let me write it out. So the curvature kappa is the magnitude of dt ds, dt capital ds. So where t is the unit vector, that depends on t naturally, but it is f prime. How do we make a vector into a unit vector? Divide by its magnitude. So we certainly have to assume, which I should have assumed to begin with, that f prime is not equal to 0. So remember that discussion that we had, that if you want to study a road, and then study the road by taking somebody driving over it and then studying his tape. Okay, so that person better not stop at any point. Okay, so once again, this is the unit vector, unit tangent vector. Remember, the derivative is a tangent vector, but it's not necessarily a unit tangent vector. And then the point of arc length parameterization was to take out of consideration the magnitude of linear acceleration, but rather only concentrate on terms. And but we are doing it differently now. So we are then making a unit tangent vector from our let's say velocity vector by dividing by the magnitude. But now the tricky part is that we actually dividing by differentiation is with respect to arc length parameter. Okay, so not the same parameter. So this is all of t. F is a function of t. F prime is a function of t. T is a function of t, but we differentiate with respect to f, the arc length parameter. If we don't, the result will just simply won't be right. Okay, so so we want to use now the result that we just had, and express this arc length parameter. The curvature, where intentionally is the variable is omitted, and express it as a function of t. So, okay, so which is incidentally curvature is a numerical function, right? Because f is a parameter curve, t is a parameter curve, but you take the magnitude, you have a numerical function. So we just write what we already know. From the chain rule. Okay, and which is then this is what we're after. This is the term we're after. That's the curvature. If we take the magnitude, it's going to be our curvature. This is we know from over there. Okay, and then this was better. The point is to express everything in this term because this is the unit vector in terms of t. Okay, so then I can just rewrite, take these two together, and what do I get? I get the formula for the curvature as a function of t. Okay, so I take the curvature. Let me just go through this dt ds. Okay, and dt ds, which is according to the previous formula, it will be ds dt dt over ds dt magnitude. Excuse me. Okay, so I spread it out. ds dt becomes the absolute value, or not. No, you don't need absolute value anymore. And so this will be t prime magnitude as a function of t. Let's make that clear now. And the denominator is right there. The magnitude of our velocity. Okay, so that is the alternative formula for the curvature. So if you look at it, so it is still the derivative of the unit tangent vector, but this time it is with respect to t, the original parameter, and all you have to do to adjust it, you just divide by the magnitude of the velocity. Let me write it out. So kappa of t is a real valued or numerical function of this. So that is what we're going to use for the purpose of for numerical analysis that I started last time. So this is a convenient formula that we're going to go through and see a few examples of computing, approximating curvatures of a variety of curves. So once again, what we're going to do is let me find this thing. For our curve, for our spreadsheet, okay, that's the one. Okay, so all right. So what we're doing here, we have a circle or ellipse depending on the choice of these axes or rather the dimensions of the ellipse. So right now they're 2 by 2. Okay, so they are parameterized in the usual way, so we're picking the standard, not arc length parameterization of our circle, same with the ellipse. Okay, then we're computing average velocity, so this is a sample. This is the sampled, sample, the x and y are sampled parameter curves, so as you can see we end up with only a few dots. Then based on those dots, remember we're doing difference quotients, okay, so to find out the rate of change as we move from point to point, and for x and then for y, and then we did the speed over here of this at x prime y prime, and as you can see it is equal to 2 because the radius is 2. Okay, so we are next going to be doing is, well, back to the formula, we're going to need f, so that's what we have found f prime, so this is f prime if you like, right? These two x and y, x prime, y prime, these are the components of f prime, the average velocity. Okay, further, this is the magnitude of f prime. Okay, this speed, right, that's the denominator. And all what remains is the numerator, the actual unit circle, unit tangent vector. Okay, so this is the tangent vector, what we just established. This is the tangent vector. Now we need to find the unit tangent vector. Okay. Okay, so that's it. Unit tangent vector. So it will be well, let's just say unit. I'll put this is going to be t. Okay, t, it will be based on f prime, remember, and so it will be x and y here. Okay, so if this is my x component of f prime, what do I do with it to get the component, the x component of the unit tangent vector? Question mark.
Do we want to we want to project it onto the y-axis, right? Right.
But I mean, the plan is always the same. I guess I just should make that point clear. Is so v is a vector. V over magnitude of v is the unit vector in that direction. In the direction of v. So this works just too many times in order to worth it writing separately in the direction of v. Okay, so every time you have a vector, you want to make it a unit vector in the same direction, to just divide by the magnitude. So and then how do we divide a vector by a number? Well, how do we divide a vector by a number? Component-wise, we divide each of the components by that number. Okay, so we have our, right here, we have our x prime, y prime, so this is the component. What do I divide by? By the speed, right? So the speed is the magnitude of the velocity, so to get over here the unit vector of this, I divide this by that. Each of these components divided by, well, it happens to be 2, but that doesn't matter, it will work for anything, and that will give me the unit vector. Well, let's just do it. So it's going to be, I'm taking this vector, this component, second, equal to the x component, and divided by the speed. Okay? So x component of the unit vector will be x component of the original vector divided by the magnitude. Okay, so the x component of my velocity will be divided by the speed in order to create the unit vector. So just to confirm, okay, so it is okay, that's right. I gotta move this thing. Okay, so look at it. It is, at least this is plausible, and I don't want to verify that necessarily, but it's plausible. This is a unit vector, right? So you take the square of one, take the square of the other, and together you will have 1. Okay, so spreading out. So these are the unit vectors. They certainly vary. There is no special way to visualize it. It's just certainly it's not impossible. Let me do it just in case. Visualize. Okay. Chart. Okay. Well. So what's so special about it? About this curve? What's so special about it?
That it has a radius of 1.
It has a radius 1, so in other words, indeed, these are vectors, and their magnitude is 1. Okay, so they just point, but really they are vector if you start from the origin towards these points, so you've got a bunch of unit vectors. Okay, so that confirms it, but this is really not hardly the answer, because now it is time to differentiate it. We got t, now we need to find t prime before we do the magnitude, and then only then we'll just divide by the f prime, by the speed. Okay, so now differentiate. How do we differentiate? Let me, okay, t, x and y here, x, y, now we're moving on to t prime. Okay, so how do we compute t prime? In the same way, same formula, difference quotient as we always have. Okay, so we already did it once. We have to do it twice. Remember, the curvature is ultimately about the second derivative. Just second derivative done the right way, but it's still second derivative, so we have to differentiate for the second time. Okay, so I'll just take these two values, and well, I could just copy. Yeah, I could just take these. I could just take this one and put it here. Okay, let's see. What does the formula say? It says correctly. So the x component of the new vector, the derivative, is the difference between t, computing t prime, computing t. From t, we're computing t prime over there. X components are subtracted, divided by the time interval. Okay? So, all right, and that's fine. And then we spread it to the right and then down. Okay. Okay, so this is supposed to be the derivative of the unit, tangent vector. Yes. Okay, so Well, I could just try and see if it produces anything interesting. As you can see, it's once again a unit circle because we are still dealing with just a circle. Okay, so let me make an ellipse for a moment. Okay, so as you can see, how interesting it is. Okay, so let's try to understand what this is. So this is supposed to be the derivative of the ellipse. Bring it up. So the ellipse that we're looking at. So this is the ellipse. It is, as you can see, stretched vertically. The parameterization starts over there, and now if we put this, if I just can bring it up, so we can put them side by side, and we can try to analyze what is happening to the unit tangent vector. So this is the derivative of the unit tangent vector again. So, so what do you see? What's happening to the unit tangent vector? So this is, once again, this is not the unit tangent vector. The unit tangent vector of will be pretty much, what is it? It's again some kind of an ellipse. So it's supposed to be the direction at which the unit tangent vector is changing. Okay, so the unit tangent vector, suppose we are looking at this point over here at the very beginning. Okay, so the unit tangent vector is vertical, right? It is vertical, and then it's turning to the left. Okay, so well, unfortunately, the match I cannot tell which values of. Okay, let me first do this. Unfortunately, it's unmarked, so I'm not sure which point corresponds to what location. But we should have a derivative somewhere among these values, among these points, that is negative. So maybe this is it. So the direction of the change of the unit tangent vector over there, is this, turning this way. So it means that its derivative is pointing in the, and it is unit 2, so it will be pointing in the directly, it will be perpendicular, and it will be pointing towards the origin. So that might be it. Once again, it's unmarked. I don't think I can find out what. Okay, maybe there's an option. Add data label. That might be it. So as you can see, it says 0 over there. Let me try again. Add data label. Okay, so yeah, I think it makes sense. I think it works out just fine. Okay, as you can see, the data label correspond to, what do they correspond to? Well, anyway, just I guess we could keep guessing, but I'm pretty sure that's the answer. So this dot over here gives me the derivative of that vector, the tangent vector, which is up there. So let me make a little picture here. So this is what I'm talking about. So this is where we are on the ellipse here. This is the unit tangent vector, t, okay? And then its t prime will be directed in the perpendicular direction towards the turn, Okay, so, all right, so that gives me the, no, that it still does not give me the numerator. This is the numerator. I still have to take the magnitude. To get the numerator, I have to take the magnitude and then divide by the speed. So let's carry that out. I think the next line will be the curvature. Okay, so I'm putting curvature right here. Okay, so I'm taking the magnitude of this vector, t prime. Okay, so it's equal to, and I'll take the square root of this squared plus that squared. Okay? And so that is the numerator. And I divide by the speed, which you cannot. I cannot put it here because I cannot click on it. Okay, so it's R, the same row, and column is 8. Wrong place. Column 8. Okay, you can see it, but it's there. Okay, so we can just click. Okay, let's confirm. Okay, so once again, the two squares of the components of t prime. Okay, divided by the speed. Okay, so this is the kappa, the curvature. Well, to confirm that the results we didn't mess up anywhere else, let me go back to circle. Okay, as you can see, the curvature is 1. Okay, so that works out. Okay, let's try curvature 2. We make the circle radius 2. The curvature is 1/2. All right, it's working out. So it is a straight line. I mean, it's constant, but at least the results are as expected. So once again, this is A and B, the two major minor axis of the ellipse. But so next stop is maybe definitely making it an ellipse rather than a circle. Okay, so as you can see, there's a variability, but let's plot it. Let's plot it so we can compare it. Okay, so I am going to plot it. Once again, insert. Oh, that's interesting. Okay, so it shows a lot more stuff because those dots are actually being repeated. So it's not one point, but it's a whole bunch of periodic behavior here. So this is the ellipse, which is stretched vertically, as you can see. Let me make that clear, because we now have to actually, the measurements do matter now. So as you can see, it's let me do even more. It's 1/2 ellipse, even more so. And now this is the initial point. We do it according to the time t. That's all the work that we did. The algebraic work pays off now because we are now doing everything with respect to the original parameter t. We don't do arc length parameter. So as you can see, what's starting point series 1.1, which means that this is where we are. Okay, and okay. So what do you see? What's happening to the curvature?
Increases, then decreases.
It increases, then decreases. Starts at the point, by the way, close to 0.2. So it's like 1/5. Remember what we know about circles. So we want to compare it to circles. Then whenever we see the curvature, we take its reciprocal, and that is roughly the circle that curve resembles at that point. Okay, so the radius of the circle over here is kind of like radius of the spot. Okay, and then it increases. Look at it, and look at it. It increases, and then at over here, what is that number? Unclear, but I mean from the graph it's unclear, but it's pi/2. This is pi/2 where our curvature reaches the highest point, and it is kind of close to 2, which means that the radius of the circle that we would put over there would be 1/2, roughly. Okay, so you can certainly make these more. You can make it more accurate. So this that's not here. So I put pi. Okay, why is it? Okay, let me try. More points. As you can see, the accuracy increases. The ellipse has more points to represent, but the idea remains the same. As you can see, it is this clearly gets to 1/4, not 1/5, 1/4, right? And the maximum over there gets closer to 2. So then the two circles that I would like to insert, one here and one there, to approximate, we don't, tangent lines approximate curves, but that's a linear approximation. If you want a quadratic approximation, then the idea is to approximate with circles. Forget about Taylor polynomials for a while. We just suppose the best idea is to approximate curves beyond straight lines is by circles. So what are those circles? Well, this is what we discovered, that the radius for a slowest circle, larger circle, this one, would be 1/4, and the bigger one will be not for 4, and the 1/2 for the other one. Okay, so that is the least we can do. The results are all here. So everything is computed here by just algebra of Excel. So the only thing that we did that actually involves the ellipse itself is right here, the sample parameterization. So we have that standard parameterization, and we sampled it. And after that, it is just difference quotient once, the normalization dividing by the magnitude, one more difference quotient, and then finally that fraction over here. That's in the very last line over here. Over here, that is this formula that we incorporated there. Okay, so certainly could. Well, let's see what happens if I put 3 here. So once again, so it's 1/2. That's the ellipse. It's stretched vertically, and the curvature runs between 1/4 and 2. 1/4 and 2. Okay, well, let me try with 3 here. Okay, so it actually runs up to 3. The curvature runs up to 3, and this one, you can guess what this is.
1/3.
Oh. Well, and then 1/9. Yeah, so I can't really confirm that number yet, but that's what it looks like. So it all makes sense, and the good news is that it is applicable to any curve that you can imagine. This one, just a place to start with the ellipse is probably a good idea. Okay, so we have the definition. We'll come back to that spreadsheet a few times. The definition of the curvature, the formal definition. The meaning of the definition that we started with previously, well, it still applies. I think it is easiest to understand. Is the rate of change of your velocity when your speed is 1. Okay, so that's the curvature. But here we redefine we had to redefine because so that we could produce a nice formula like this. So, and then the formula that was applied that produced the results, the spreadsheet. Okay, so well, a couple of more words about this, just to refresh your memory that then the curvature is, so this is a turn, which is what we just talked about, and this is the curvature, and then you turn faster. The curvature turns faster, and so this curvature is larger. Okay, 1/kappa is called the radius of curvature. Okay, radius of curvature meaning the there is a circle somewhere which is also still to come, and you can try to approximate that. That is the idea of once you know the radius of curvature, this is what you do. You go perpendicular to the tangent like this by r, okay, and then the idea then, well, this is not, I didn't do such a good job, like this, okay, and then my radius of curvature will be like that. It will be nicely approximating my curve at that particular point. Naturally, you have a bunch of those points as you move on and on. So this one, so this is R. In this one, you will go farther, and the circle will be bigger. Okay, and that brings you to the idea of well, not the fact that remember that the straight line has zero curvature, but this is the radius of convergence of curvature is also I should remind you of the idea of a turning circle. Remember, I brought it up some time ago. So one thing, well, if you want to, so question is how, depending on what kind of car being driven on the street, how do you turn a 90-degree turn? What kind of curve it should have? Because you could do it this way, or you could do it that way. Okay, so how much do you need in order to make a full turn? How much of a circle you need over here? So either it is a small circle like this, or it might be a large circle, and that depends on the circumstances. And usually that's the radius of curvature is a number that is more commonly used, especially in engineering applications, because you can actually test it. You can take your car, turn it the wheel all the way to one end, and make a turn and measure what kind of circle you have traced, and then you'll know your radius of curvature, as well as now you know what the curvature is going to be. In fact, if you think about it, a turning circle might come up elsewhere, and this is the next topic that we are starting, and that is in three-dimensional curves. So if you have a narrow street and you want to make a turn like this, if you know your turn circle, then you know whether or not it's possible or not. Okay. However, now what if we are doing something related, and that is like a ramp, a circular ramp. You know, like old-fashioned ramps in parking garages that you actually will make full circles like this. Have you seen that? I haven't seen those in a while. But then once again, its radius is determined by how much the turning circle you expect to have those cars to have. Okay, so and the question is, so suppose you have a turning circle. This is a turning circle which fits the street. Okay, so a car, suppose this is R. Okay, a car can turn. Suppose the car, particular car we're considering, and its turning circle is R, so that it could make a full circle with the street that has depth 2R, right? So that's your turning circle. That is your radius of particular radius of curvature. But then now, when you have a ramp, the curve is now three-dimensional. Okay, we haven't seen a lot of three-dimensional curves yet. But you can imagine, so this is above you. This is you from above on the street. So this is the street. But what if we're looking at a ramp, circular ramp? So it fits inside of a. It fits inside of it's like a tube or a cylinder. Okay, and then it will follow like something like this. Okay, so it's once again a helix, and then now the question becomes, what should the radius of this kind of cylinder be in order to accommodate the exact same car as this one? Okay, so we know the radius of curvature of the car or cars that are to use this parking garage, and now we want to know what should our or be here for our ramp. So the question is it larger, same, or smaller?
I would say it's smaller, right? Because you're as the car travels up the helix, you're making the turn, but some of that turn is being made with
Well, first of all, correct. It could be smaller. Okay, why? Because you have more room. Roughly speaking, you have more room when you're moving up. Why you can be more specific? It's because you're not driving like this. You're driving up, which means that that circle that we just talked about is not actually it's not horizontal. It will be inclined. So you could fit inside of a smaller cylinder. You can take this circle over here, and you can fit it like this. Well, not exactly. You're not going to fit. It's actually if you cross the cylinder, you're going to get an ellipse. But the point is that you're going to have a radius of convergence here. This radius of curvature, the same as a smaller circle. Okay, so then if my circle, which is actually an ellipse, has this is inclined, then the radius of this one is smaller. The base of the cylinder is small. So we're gonna demonstrate this next time more precisely without it. Okay.